Okay, so let's read through the problem. I'll just read the problem out loud. It says a player kicks a football from ground level with an initial velocity of 27 meters per second, 30 degrees above the horizontal as shown in the figure, and I'll redraw that figure. Find the ball's hang time, range, and maximum height, and assume that air resistance is negligible. So there will be a problem just like this on the test next week. So we've got a football that's being kicked at it's at a 30-degree angle, I believe. So here's the initial velocity of the ball. So you kick the ball, it has a magnitude and direction, right? Does that make sense? So V naught equals 27 meters per second. This is what's given. And this is 30 degrees. All right, that's the angle that you've launched it, the launching angle. Okay? Now the ball, you know the ball's going to go, it's going to go up, and then gravity bends the trajectory down. So it's going to go up and down. And what we want to find for this is the ball's hang time. That's the time that it's in the air. That's hang time. That's important in football. When you kick the ball off, you want to have as much hang time as possible because you want to give your players time to run down the field to tackle the guy. And then you want the maximum height. I'm going to call that Y max or delta Y max. That's your maximum height above the ground. And we want to know the range. And I'm going to call that delta X. The range is delta X from here to here. In other words, how far from where you kicked the ball did it hit the ground? That make sense? Okay. So you have to understand that vocabulary of like what they mean by hang time and maximum height and range. Okay? And so let's solve it. So now here's the thing you have to know about this type of problem. There's some tricks to solving this. They don't really tell you in the problem, but first of all, you know what the acceleration is, right? The acceleration is negative 9.8 meters per second squared. But that's only in the y direction. What is the acceleration in the x direction equal to? In the horizontal direction. Once the ball is in the air, once it's left the foot of the football player, if you're looking at the ball somewhere in mid-flight, and we're neglecting air resistance, the whole point of projectile motion is that there is no acceleration in the x direction. Does that make sense? Yeah. The only thing that's pulling on the ball is gravity. Once it's left the foot of the football player, it's just in free fall. The only thing pulling on it is gravity. So what that means is that the velocity in the x direction doesn't change with time. But the velocity in the y direction obviously does, because gravity slows it down. As the ball's going up, it slows it down, and then it pulls it back down to Earth. Okay? So you know these things, even though it didn't explicitly tell you. You just have to know that you already know that. Also, at the maximum height, you have to know that the velocity in the y direction is equal to 0. Because the ball was going up, but now it's about to go down. And in that instant in time where it's changing direction from going up to going down, you have to stop for an instant in time. It has to be, it's not moving in the y direction. Now in the x direction, it's still moving because there's nothing to slow it down in the x direction. So whatever the x direction, the horizontal velocity is, you keep that the whole time. Make sense? Now here's another thing. you can take this velocity vector here and break it up into its components. There's the velocity in the x, v naught x, and this is v naught y, like this. And you have to know, oh, to get v naught y, I take v naught, which is given, and multiply it by the sine of the launch angle. Right? Because when you take the initial velocity and you break it up into its x and y components, it makes a little right triangle. And this is the opposite leg of this right triangle. And the way you get the opposite leg is to multiply the hypotenuse by the sine of the angle. And then this, the velocity in the x direction, is equal to v naught times the cosine of the launch angle. Now this one doesn't change. The velocity in the x direction is going to be v naught cosine theta the whole time. Okay?
But for like previous problems, we had mg sine theta. Why is it v naught?
Oh, the mg sine theta, that was in an inclined plane problem. So this is not an inclined plane problem, totally different problem. And it's the right triangle. You look at the triangle and where the angle is that determines whether it's sine or cosine. See, here's the triangle I drew. I mean, I'm given this initial velocity and I want its horizontal and its vertical. Well, this 30 degrees is measured from the horizontal. So thus, this is the adjacent leg, which happens to be the x component. The y component here happens to be the opposite leg of the right triangle, and that's why you use sine theta. So in that inclined plane problem, the angle was measured from the vertical, not from the horizontal, and thus the sine and the cosine kind of got switched.
Yeah.
But you're still using cosine because you're dealing with the adjacent. You're adjacent to the angle. You use sine when you're opposite from the angle. Well, let's solve for time. Well, here's another thing you also know. That when you go from here to here, what is delta y equal to? They don't tell you what it is, but you know it. What is your change in y? If you start at the ground and you end at the ground and it's level ground, it's 0, right? So your delta y is 0. Legos. I think under that drawer down, yeah, look under the sink. Should be a big thing of Legos down there. If, yeah. Okay, so let's take a look at the time here. Well, you know delta y. Now, here's the thing. I want to know how much time it takes to go from here to here. What do I know? I know delta y. I know the acceleration, and I know the initial velocity. And I want to find time. I can use the third kinematic equation, has all of those. So you still have to use your equation list. So you go delta y equals v naught y times t plus 1/2 a t squared. Now what do I know? I know that delta y is 0. For the, if you do the whole hang time, your delta y is 0. V naught y is just 27 meters per second times the sine of 30 degrees, right? V naught sine theta times time plus 1/2 a is negative 9.8 meters per second squared times time squared. Now all I have to do is solve for time because I know everything. Well, how do I solve for time if it's in both terms? Well, first of all, let's divide both sides by time. And notice over here, 0 divided by time is still 0. This is just 27 meters per second times the sine of 30 degrees But now time cancels out, see? Time cancels there, and it also cancels with the time squared. Well, let's just put minus 1/2 9.8 meters per second squared times time. And now I can solve for time. Put this on the other side. Well, what is the sine of 30? It's 1/2. What's half of 27? Is that 13.5? So I'll put this on the other side, negative 13.5 meters per second. Now I want to solve for time, so I'm going to multiply both sides by 2. And then divide by negative 9.8. And let's see, the negatives cancel. And I'll get my calculator out. And you get 2.76 seconds. See, the meters cancels the meters. The second cancels with the second squared. You have 1 over seconds, which you reciprocate and multiply to get seconds. So there's my time. That's not a great hang time for a kickoff. The coach would not be happy with that. A good hang time is like 4 seconds, 4 or 5 seconds in football. Okay, so we did this one. Now we want to find delta y max. Now we have a couple of choices because now we know what the time is. I don't like using the time though, because what if I made a mistake in calculating the time? I don't want to have to use time. All right. So let's take a look at what I know. I know the initial velocity. I know the final velocity in the y direction is 0. And I want to find delta y, and I know the acceleration. So what equation doesn't have time in it? Use the fourth kinematic equation. Let's see, am I still on screen here? I'll start right here. Final velocity squared equals the initial velocity squared plus 2 times the acceleration times our change in y. Well, we know that when the ball gets to the very top, the final velocity in the y direction is 0. And I know what this is. Now let's solve it for delta y. Well, you got to bring this to the other side. And then you have to divide by 2 times the acceleration. And now I'm ready to plug in my numbers. It was, what, 13.5? Remember how I got v naught y? V naught y is 27 times the sine of 30. And the sine of 30 is 1/2, so I just divided 27 by 2. But I have to square it, and then I have to divide by 2 times the acceleration. But the acceleration is just the acceleration of gravity. And so now I'm ready to solve for delta y. So I'm going to go, first of all, the negative goes away. Got to square that. Divided by 2 times 9.8. And you get 9.30 meters. So it's going to be a little under 10 meters high. Does that make sense? Any step in here? Follow each one? Okay. Now finally we need to figure out what delta x is. There's only one kinematic equation in projectile motion for delta x. And that is delta x equals v naught x times time. That's it. You could say, well, what about this? Plus 1/2 ax t squared. Well, yeah, what is the acceleration in the x direction? 0. So this whole term goes away. So I know what the initial velocity in the x direction was. It was 27 meters per second times the cosine of 30 degrees. You can't use 27. You have to use the horizontal component here. Times time. Now you have to use the time you calculated from the first thing we did. There's no other way to do it. And when we do all that, my calculator, 27 times the cosine of 30 degrees times 2.76. And you get 64.5 meters. Now, that's not bad. That's a pretty good distance. Geez, that's about almost 70 yards. So, I don't know, where do they kick it off from? I forget what yard line there is in a kick. You go to all the football games, right? But the problem with this is that the hang time is so low. This is like a line drive kick. Opposing teams love this kick, love to receive a kick like this because the other guys haven't had enough time to get down the field, so now they can get a really good return, return in. So there's a little physics in football. So that's all. Now let me check the work. Yep, those answers are all correct. Check them all. Okay?